Welcome back to the classroom. My name is Mr. Wong, and today we'll be looking at kinematics. The specific inquiry question we're looking at is from inquiry 1, and its focus will be on the calculation of relative velocity of two objects moving along the same line using vector analysis. So we'll look into what is vector analysis, and just to talk about, if we're talking with movement in the same line, we're talking about it in one dimension. So this is relative velocity in one dimension. So let us begin. Okay, so when we're talking about relative velocity, we need to firstly discuss a concept known as a frame of reference. So in this scenario, I have a stationary observer, I have one bike rider, Yari, and I have another bike rider called George. So Yari and George cross paths in exactly 1 second. We want to actually see, based on the frame of reference of these three observers, how differently does the velocity or the displacement appear to that specific observer. So the first one we're going to start with is a stationary observer. So you can see, according to the stationary observer, the reason why we call them stationary is obviously they're not moving, and they are measuring the relative velocity and motion of the two bike riders. So they appear as Yari appears at 7 meters per second. You might not have noticed, but George started at 10 meters per second. So George is relatively faster than Yari, as you can see with the green line being slightly more steep than Yari, the red line here. So there's that. Let's try and change our frame of reference and see how this sort of scenario goes from there. So this time we're going to use Yari's perspective. And as you can see, according to Yari's perspective, because Yari is moving towards George, it would appear that George is coming much faster at Yari. Okay? And you can also see from this reference, in Yari's perspective, if they are moving at a constant speed, they would feel like as if they aren't moving at all. So, how to put it? If an object moves at a constant speed, that could be not moving at all, then they would feel as if they are stationary unless they look at their surrounding frame of reference or other frames of reference. So you can see, according to his frame, George looks to be moving much faster towards him. If I move the observation to George, George would feel as if they are the stationary observer, and they would feel like Yari is moving much faster towards them. Okay, so that's what we have here. Now let's go back to, or let's use this scenario. So at the start of this, Yari is moving at a velocity of 7 meters per second. George, on the other hand, was moving at 10 meters per second. Now they are moving in the opposite directions of each other. So let's say Yari was moving in the negative direction and George was moving in the positive direction. If we compare the velocities, so according to the stationary observer that we had before, Yari was moving negative 7 meters per second and George was moving plus 10 meters per second. However, if we then use George as the observer and we ask the question, what is Yari's velocity relative to George? Okay, so we can clearly see he's moving a lot faster. So he's clearly moving at a speed higher or velocity higher than -7. Okay, so we'll look into how we do that calculation. But according to George, Yari would actually be looking as if they are traveling at negative 17 meters per second. We'll get into the logic in a second, but hopefully you can sort of gauge how we came to this value here. Okay, so let's just quickly cover what a frame of reference is. A frame of reference is a coordinate system that we use to compare motion of one object to a fixed position. In the three scenarios that we looked at, we had the stationary observer and we had the two bike riders. Each person or each observer will see as if they are in that fixed reference point, and they do their comparison in motion with other moving objects. So, as you will know, with the kinematics equations that we've done, the three kinematics equations, you might realize that the frame of reference we've been using is actually the ground. Okay. However, we've never used the kinematics equations to reference another moving object, and obviously we won't be doing that. That would be a bit too difficult. But we are going to look at cross-referencing the relative velocities of one moving object in comparison to another moving object. So let's start again, and we're going to look at this motion here. So we have two cars. Okay, we have the red car that's moving at plus 100 kilometers per hour, and we have a green car that's moving at minus 90 kilometers per hour. If we're looking at vector analysis, this is how we can look into it. So imagine 1 hour has passed. Let's imagine the two cars are side by side each other. This is the direction that the green car goes, and this is the direction that the red car goes. Okay, they both start from a displacement of 0. I'll let 1 hour pass, and the green car has traveled 90 kilometers in this direction. The red car has traveled 100 kilometers in this direction. If we look at the overall resultant vector, or the the sum of all the vectors, the perspective would be like so. So according to the red car, the green car has in 1 hour traveled 190 kilometers away from the red car. Okay, so according to the red car's perspective, the green car is traveling at 190 kilometers per hour. That's kind of how we can make that assumption. Cool. So the opposite of that, or the alternative of that, is that the green car, according to the green car's perspective, after 1 hour, the red car has traveled 190 kilometers, and so it also sees the red car have a relative velocity of 190 kilometers moving away from it. So this is how we can analyze it if they were moving in the opposing directions. If we want to express this mathematically, we can write it as the velocity of v1 to v2. So it could be, the question could be worded like this: find the velocity of car 1 relative to car 2. So car 2 is the perspective, okay? Or we can say car 2 is the frame of reference that we care about. So this is what we call a vector subtraction. So we're going to subtract, so we have v1 subtracted by v2, okay? So if they're moving in opposite directions, we can express the following. So we can say that if they're moving in the opposite directions, then v2 would be negative, okay? So that's what we have. and then we can express the equation like so. So let's just quickly summarize what we have here. This equation is the general equation to describe the relative velocity of one object compared to another. If they were moving in the opposite direction, you essentially add the vector arrows together. So let's see how that works, because this is kind of what we did in the previous example here. So let's imagine we have two cars. One's moving at 100 kilometers west. The other is moving 90 kilometers per hour west as well. If we draw out the vector arrows, this is for our 100 kilometers per hour car. This is our 90 kilometers per hour car. They're both moving in the same direction, okay? The question is, what is the velocity of car A relative to car B? So I want to know this frame of reference. Okay, I want to know that frame of reference. So according to car B, which is this arrow down here, it's still trailing car A by about 10 kilometers after 1 hour. Okay? So if it's trailing car A after 1 hour by 10 kilometers, that means, according to car B, car A is moving 10 kilometers per hour west faster than car B. So that's how we could say that. How about the perspective of car A? So let's change the color. So what about the frame of reference for car A? How fast would car B be traveling? Well, if we have a look at the arrow here, let's imagine we're car A here after 1 hour. We look at where car B is, and we can see car B is about 10 kilometers slower than us. Okay. So if car B is 10 kilometers slower than us, it would almost appear as if car B is moving away from us. So in this case, car A's perspective would see car B moving at 10 kilometers per hour east. It sounds weird because we know that if I'm a stationary observer, car B is moving in exactly the same direction as car A, but that's not the perspective of what car A sees, because they're looking backwards to the position of car B. So car B would always look like it's going away from it or behind it. And so that's how we look into that. Okay, so let's look at the vector analysis for the opposing directions. We talked about this before, but we can have a look at it again. Okay, so the general equation we use to describe relative velocity is, if I'm trying to find the velocity of the green car relative to the red car in the analysis, that always comes second. So this is the perspective I'm trying to work out here, right? So the red car is going in this direction. The green car, let's say, is going in this direction. It doesn't really matter which one you want, but let's just say that's the case. I want to highlight this vector here. Remember, velocity is a vector. Okay. If velocity is a vector, that would mean okay, so let's look at our example if the object is moving in opposing directions. Our red car is moving in this direction here. our green car is moving in this direction here. You can see the arrows that we've drawn out here. So what we have here, red has gone in this direction. Green has gone in this direction here. Okay. Okay, so let's have a look at the relative velocity for opposing objects. So we have the red car here, in this case, moving at 100 kilometers per hour in this direction. And we have the green car moving at 90 kilometers per hour, moving in our left-hand direction. According to the red car, this is the perspective I want. So I'm calling this frame of reference, or 4. If I stop everything after 1 hour and have a look back, the green car would have appeared to have gone 190 kilometers in that particular direction. Let's call that the negative direction because that's what we set up here. And so that's how we work out the relative velocity of the green car relative to the red car. This is how you can use vector analysis. You draw your arrows out and then you apply it to the question, or you find the resultant velocity from there. So let's try some questions and then we'll see how we go from there. Okay, so the scenario we have is car X is moving at 40 kilometers west. So I can draw this vector out regardless of the question we're looking at. Car X is here, and then we have car Y. We'll try and do it in a different color so we know the difference of the arrows. Car Y is moving on the same road, but 60 kilometers per hour east. This is what we have here. It says calculate the velocity of X relative to Y. So we're looking at from Y's frame of reference. Here we're looking at X's frame of reference. So if I look at car Y's frame of reference, car X has moved 100 kilometers westward from it. So we can say that it is 100 kilometers per hour west, or I could alternatively say negative 100 kilometers per hour, because we're going to say this is the negative direction here. For our scenario down here, if we're looking at car X, then clearly it's gone in the other direction. It's still the same distance afterwards, so we can just say that it's 100 kilometers east, or I can say it's plus 100 kilometers per hour. So that would be the idea that we have there. If we want to try and solve for it using vector equations, let's look at this example here. So according to Vy to Vx, Vy has a velocity of 60 kilometers east, okay? Or so to speak, we could say it's plus 60, okay? Car X is moving 40 kilometers. So using our vector analysis, negative 40 kilometers west. Now west is a negative value for us, so subtracted by 40, okay? And we'll find that we get a value of positive 100 kilometers per hour. And so that would also imply that it's 100 kilometers east. And so that's how you can go through a question like relative velocity using vector analysis or these vector equations that we have. I'll take you to our summary page. So onto our summary page, these were some of the concepts that we discussed in today's theoretical lesson. I will do a separate recording for the questions related to this lesson that will come out right after this. So if you found this video useful, like, subscribe, and I'll see you in the next video.